Hello. Yes, it works. Good morning, everybody. I hope you also enjoyed so much the conference dinner yesterday, and that you are ready for another day of our conference, in which we start with the keynote from Angela Verschoor. I will shortly introduce her, only shortly. Angela is working at CITO, that's the Institute for Educational Measurement in the Netherlands, and she has a background in mathematics, and she finished her PhD on the subject of say optimal design, optimal test design, automatic test construction, and she has already an experience of more than 20 years in not doing only research but also developing operational CATs, and she told me a few minutes ago that her first one, which went really in production, was from 1995, and I think she will share her experience with us in the talk she will give now. Angela, start please.
So this is, let's say, our ambition. And the road from this little kitten to this big tiger is not always easy. I'm not going to present you a cookbook recipe how to do this, but I'll share a few experiences over the last years how to get there. And my role, CITO's role, usually is one of a contractor. Sometimes we produce tests, also CATs ourselves, say in-house, but usually most contracts come from external parties. And in Europe, where we come from, that usually is a government party issuing a tender. And you find a few keywords there. Of course, scalability. We have the ambition to have, let's say, 10,000, sometimes 100,000 concurrent students at the same time working. We have a population of, let's say, 2 million test takers who want to take a test or need to take a test in a few weeks' time. They also have a clause usually saying something like, well, if we don't like your product, if it doesn't work, we want to switch. And not only should that be a legal possibility, it also should be a technical possibility to switch relatively painlessly from one system to one platform to another. And transparency. People don't want to buy a black box with a box of tricks. They want to know exactly what's inside, what is going on. I think this is also part of the origin of the financial crisis, where all these nice models about investments were so opaque that no one knew what was going inside. We don't want to have a financial-like crisis in education, in assessment. So, transparency is the third important keyword that you find. Scalability. If we're working in a lab, we may use some simulating situations, some simulations. Well, that usually is one simulated student at a time, working on a test in hopefully a millisecond, and then the next millisecond, the next student comes in. Now we're working with, well, let's say, 10,000 concurrent students, all wanting to have an item at the same time. We need parallel architecture for that. Well, that's not my profession, that's not my expertise, that's expertise of software architects, but we need parallel algorithms, also parallel selection, item selection algorithms. Usually this is done in the form of stateless algorithms. We have in the architecture a whole set, a whole array of algorithm instances, and every instance need to be able to answer any request coming in. So normally when we are talking about an algorithm, we think about a nice flow diagram and a nice, let's say, dialogue between a player and an algorithm. Something like this. The player just asks to its algorithm, well, hey Joe, do you know Sophie, who is working on the computer? Can you tell me the next item? The algorithm starts to calculate and comes back with an answer, item, let's say 23. But now the situation is different in parallel architecture. And just imagine that all of you are algorithms. You're working on a calculation, some of you are just available at the moment. And I walk in and I'm a player, and Sophie has answered her question, and I, as a player, have a question for you. Is there a volunteer? Who is available for me and who can answer my question? What is Sophie's next item? And let's say that Theo answered the question before, but now Theo is just very busy making a calculation for quite someone else, so someone else has to take over. What do you need? Information. Think about it yourself. It's very easy. You need to know, okay, what is the test that she's working on? What are the items that I can choose from? And also very important, she has already answered these questions with those answers. So the player has to give all this information to the algorithm, and then the algorithm can answer back, let's say, item 75. And then, so much time later, the next request comes in. Those algorithms are, in terms of flow diagram, nothing else than what we've seen before, but just the mechanism is different. So we have a start. Usually, when we see these flow diagrams with start, people think, well, this is selecting the first item, usually a random selection. If the algorithm presents an item, okay, fine. The player puts the item text on the screen, waits for a response, possibly scores the response, and that goes back to the algorithm. Algorithm starts to make some calculations about ability estimation, makes a decision. Do we need to stop? That may be yes, that may be no. If the answer is no, not time to stop, then the next item will be selected. And then, of course, after that, the player takes over again, presents the item, waits for a response, etc. Until at a certain moment, the stopping criterion has been reached, and at that moment, it's time for a report. Sophie has done a good job. Maybe Sophie has done not such a great job. Who knows? And now, in this parallel architecture, we have multiple instances of algorithms, and any algorithm should be able to answer this question. And actually, this situation, I modified it already a little bit from the standard situation, needs one small modification again, and we're almost done. There's usually one entry point in the algorithm and one exit point in the algorithm. So instead of having a specific starting rule, there's just one entry point into the algorithm. That's usually called get next item. Just give me the next item, please. And the algorithm should know that it starts with a random selected item first, and all the other criteria. And then it comes back in the same way, Also, give me the next item, please. So, not so much has changed in terms of formulas. Well, the formulas didn't change at all, of course, but also the flow just needs a little modification for a stateless algorithm. Actually, being stateless comes in certain flavors. Officially, if you talk to someone from the IT, a stateless algorithm is an algorithm that has absolutely no memory. So it doesn't keep anything into memory from one call to the other call. That means that here we have a player, an item bank, a database, and there's a connection between the two, and the CAT algorithm needs all information, usually its own little database with items, their properties, which is in fact also a little database. And with every request, the entire item bank, the entire item pool will be sent over. When the call's done, the algorithm clears its memory, doesn't know anything anymore, and is ready to receive the next request. Well, intuitively, you'd say this is very nice, but it costs a lot of performance. You need a lot of computer capacity to do this. Well, that's true. That's also the reason why there are certain variations, certain hybrid situations. For instance, the right one, where the request is very small, and the CAT algorithm has its own local database. So at least we don't need to send all that information over the line every time. And it usually works a lot faster. Although there's a trade-off. The little cat here needs to access its database, and that costs time too. So being stateless is not necessarily a black and white thing. We can have some variations in there. Well, next topic, standards. I already told you, especially in the European government agencies, they want to have flexibility. If you don't deliver what you promised, they should have the possibility to move out quickly, painlessly, and find someone else to take over your job. However painful that might be to you, it is something that we have to work with. In order to do this, there are, fortunately, standards. It means that this little cat engine, the algorithm, should be able to communicate with any type of player, not only a player from manufacturer A, but also manufacturer B, or any. And this is where QTI comes in. But QTI, if you have a good look at the definitions that are defined in QTI, you'll see that everything is centered around linear tests. If you ask someone what is a test, the answer, apparently according to QTI, is, well, a test is a series of items. They're put in a certain order. You get the possibility as a student to navigate, or maybe not. You can do this, you can do that. Everything is in the context of a linear test. But in our world, in adaptive testing, this doesn't do. I would say, in our world, a test is simply an item pool and an algorithm. And the algorithm takes care of the actual test administration. This also means, by the way, that an algorithm is part of the test content, not part of the IT infrastructure. And that's also what you see in QTI later on. It is coming soon. People are working very hard on it, and actually I am not part of a work group working with it. I didn't see Michelle Barrett. Is she here? Yeah. Well, as far as I know, Michelle knows a lot more about what's going on in the IMS work group, so if you have any specific questions, I'm quite sure that you'll be able to answer them for me. But it is an open standard, because there are so many algorithms, and people in our community are working daily on research, finding new algorithms, finding variations. So you can't put everything in stone and say, well, this is what we're going to do, and this is how it should be done until the end of days. No, it needs an open standard. That means that in this communication line, there will be some tags called QTI metadata and QTI usage data with the item properties and the properties of the session, the student, the items that the student has taken before in this session. Well, that's one possibility. Other possibility is that there's a location mentioned where you can find, where the algorithm can find this data. And for the rest, there's of course, a strict protocol how these two should communicate. There's nothing saying in this protocol very specifically that you should use maximum Fisher information. No, that's all part of the test itself. This way, it is possible to create a black box. The player doesn't know what the algorithm does, doesn't need to know what the algorithm does, and that's quite okay. And as far as I know, also IMS refers to this situation as a black box situation. And personally, I'm not very happy with that, and you'll see that in a moment. I prefer to use the term encapsulation, because if you have a black box, you don't want to end up like this situation, like Schrödinger's cat. Don't know if you're familiar with quantum mechanics. This is a famous experiment, or a thought experiment, I'd better say. And in quantum mechanics, it might be quite all right as long as you don't observe, if you don't open this box, that the cat is both alive and dead. That won't do in our world. And also, especially stakeholders, the client, they want to know exactly what's inside this box. Is this cat alive? Is it dead? And that was essentially only one solution to this, that is open source software. But most algorithms in the market are proprietary and not open source. So we'll have to fix that. Either for operations, we have to use third-party open source software, let's say freeware somewhere, or if we have our own algorithms as contractor, we have to publish them and make them open source. And that is what CITO did in this case. Well, that was mainly the IT side. Then we have some other challenges to go. And one of them is very nicely phrased in a nice saying, cats like a big pool. Something like this. Well, actually, this cat looks quite happy in its big pool, but it gives me a backache. It feels cramped. And Mark Rico's told us about this index of adaptivity. This might be a situation that the cat needs 20 items and the pool has 21 items. Yes, formally this is an adaptive test, but probably with an index of 0 or very close to 0. This is more what we like. A big pool, and the cat has all freedom to swim around, even if it looks a bit anxious to me. Maybe because of the question that we now have, where do we find the resources? And mind you, this is not our ambition. This is not what we want to reach. We want to reach this. And believe me, cats, like tigers, love big pools, big way. So we had one of our tests years ago, had a test for adult education. We had a total population of about 1,300 students every year. We needed an item bank, we needed pre-tests, and we made our calculations, and we needed a sample of at least 4,000 students. So it took us 3 years of pre-testing every student. No sample, but 3 populations. Well, we did it at the time, but it got us a delay of at least 2.5 years. There are more people. I spoke to some people who have small groups. They want to produce a nice cat, but don't have the facilities, just like we had at the time. And they don't have 1,300 students, but they may have 100 students, or maybe even 20 students. So it's a matter of, well, not only budget, financial budget, but also reducing the burden of pre-testing, that we could use mechanisms like online calibration. There are a few methods. I mentioned 4 of them. Elo is, Arpad Elo was a mathematician who devised chess ratings. And if you have a good look at what he did, then you'll see that it is essentially a Rasch model that he uses. A calibration, yes. It's not maximum likelihood calibration, but it gives an estimation for, in our case, a B parameter and a theta parameter. We could use JML, joint maximum likelihood, or we could use MML. Fourth option, once we have an item bank in operation and we need some additional items, we can use seeding. Just administer 1 extra item just for pre-testing purposes. Now we may save on budget and on sample size, but at the same time we have another price to pay, especially in the beginning when our parameters are very uncertain. We're going to lose accuracy or efficiency, which is the other side of the same medal. So we have to solve that. But let's have a closer look first to Elo. I don't present you the formulas, but they're very simple. I have a few scatter plots for you. You'll see the same simulated item bank here, 400 items. And the scatter plots have the true beta against the estimated beta. Test length 20 every time. No further restrictions on like content control. And we started here with Elo with all B parameters being 0. And after 1,000 simulees, you see this scatter plot. There is a little bit bias here, still. It's not entirely aligned with the identity, but it moves very slowly towards the identity. So it does its job. Maybe a bit slow, but it works. And you can see that at the right, 4,000 simulees. it has converged quite nicely with an RMSE that I would say is quite acceptable. Also a nice correlation between the true values and the estimations. And please have a good look at those numbers. We'll see them again later on. So this is an option, even if it is maybe a bit slow. JML. Is there anyone out here using calibration of CAT data with a JML? Well, I don't see any reaction, and I think that's a good sign. Because if you do that, and Theo proved this approximately 20 years ago, you'll get bias. And that's what you see here. You're off. Yes, it is a fast method. It takes few iterations, very simple iterations, but it doesn't do anything. Or, well, let me be honest, it does something, but not well enough. But since the correlation is very high, we thought, well, okay, we can use that. What if we have a limited pretest with, let's say, known item parameters? Then we can use those to make a small model of the bias and get a linear transformation from this scatter plot to that scatter plot. Theoretically, 2 items will be enough to do this. Well, in practice, I would say if you ever want to do this, use at least 20 to 30 of them. And you'll get, if you do that during every iteration, you get this. And if you have a good look at the RMSE and the correlation, you'll see that after 1,000 students, the situation is already quite a bit better than the ELO method. So if you know how to handle this situation, it works. And if I go back here, one moment, you'll find those results here with 4,000 simulees. You'll find them in JML at approximately 2,000 simulees. I didn't show that here, but you probably can imagine that that would be the case. Well, MML does a better job. And that's not very surprising, I would say. And here you'll find the same numbers after 1,000 simulees. So yes, MML is the way to go. There's only one catch. It's slow. We never tried to use MML in a real-time situation. We never considered it. So we settled at a certain moment for a JML with those reference items. And in order to get things starting up, we use ELO at the very beginning. And that seems to work. Well, another, well, not so much challenge, but something that needs some attention. As you see, even those small little cats need some debugging in the form of simulations. And that's what the pre-conference workshop was about that Theo and I gave. So, how should the algorithm function exactly? Which settings, which starting rules, which stopping rules do we need exactly? Do we need exposure control? And how do we do it? And I was happy to hear that Juan Barada yesterday came to the conclusion that the eligibility method was quite a good method. That is also a method that we use for some slightly different reasons, because in real life situations, it is more stable than Simpson-Hatter, where you use also simulations that might be slightly wrong, because population behaves now slightly different than the simulated population, and your parameters are slightly off. No, with a dynamic method like this eligibility method, you always have the proper parameters in there. And for those situations, you have this QTI usage data. Well, last thing that I want to discuss here is people saying, well, CAT is very nice, but it takes a lot of performance. It's slow. You need huge computer systems for those 10,000 concurrent students. Or you can use a fast method that is not so flexible, not so agile. Actually, I don't think that this is really a black and white situation. It's shades of gray, yes. It is not necessarily so that an item level CAT is very slow and that, let's say, a multi-stage test is not flexible at all. Yes, you have to compromise a little bit on those things. But having said that, there are still very good reasons to choose an MST, for instance, or an item level CAT. I would say, big advantage of an MST is that it is designed and generated up front. Let's say in the back office, not real time by a computer, fully automated. On the other hand, optimization of a multi-stage test is still an art. We still don't know exactly how to do it. That was also one of the things that Mark Riekes told in his presidential address. He didn't know how to get to an MST. Well, I have not the answer for Mark, but I'll try to give an answer on that, and that is what I'm working on right now at the moment. That is an automated assembly for multi-stage tests. And we could formulate this in words quite easily. There's a target for the expected test information, the blue line with the dots, or evaluated on the dots, and try to maximize that given the, well, I'd say usual constraints like a test length, content constraints, item usage if you want, and all other constraints that you want to put in. And in this case, you'll see the green graphs. Those are the path information functions for every path. This is a 133 design, by the way. And the red one, that is an example of a realized expected test information function. So I hope this will be the first step into a long way of development of optimizing MSTs. And with that, I'd like to thank you and give you just one advice. John Barner told me this morning that you have to listen to your animals. And if you have a well-trained tiger and you've listened good to this cuddly animal, then you'll realize that it really is a cuddly animal. Thank you.
Thank you very much, Angela, for your presentation. Are there any questions or remarks, or who wants to say something? Mark.
I wanted to just make a comment about transparency, which I think is a very good goal, and we need to work towards that. But when I was working at ACT, we designed a adaptive testing system that was called Compass, which I think is no longer being marketed, but was marketed for a long time. And when we first produced Compass, we made the system very, very flexible. This was let's say it wasn't a high security system. It was designed for placing students who'd been out of school for a while into courses at two-year colleges. And so if they cheated, they would be placed into a higher level course, and so it was to their benefit to be more accurate in their response rather than to try. Maybe they would might cheat in the other direction and get a low score so they'd get an easier course. But they were paying for it, so generally speaking, people were honest. We didn't worry about security. But we tried to make this flexible for the users of it, which were the two-year colleges. And one thing we did is we made an option for them where they could specify the probability of correct classification for the persons into a course. And when we first put this out with this, plus a whole bunch of other options, and we had a big manual for it and everything else, what they invariably did is they said, well, we want to have 100% correct classification, so it made the test length infinite. And so we had to go back into the system and then start adding things in it to make it more user-friendly in the sense of when they put in this number, that it would give them an expected test length to go along with it so that they would have some understanding about what they were doing when they were trying to adjust the parameters for the way that the adaptive testing system worked. So they had to kind of have a issue of testing time and cost versus accuracy. And we had to somehow teach the administrators at community colleges, two-year colleges, how to understand all this. So it was an attempt to be really transparent, but it turned out to be very, very difficult. What we really needed to do is to take all of them, bring them in, and teach them a course so that they would understand what the system was that we had made so very flexible and we thought easy to use and do everything in the world for them. So I'm trying to get, I guess the question that's embedded in all this is, when you think about transparency, how do you think about implementing this in a practical way that the people will understand what they see when they're looking through this glass box at what is inside and all the working parts of it?
Well, in terms of transparency, I think more about the stakeholders, the test owners. Of course, students are stakeholders too, and yes, they need to, or they have the right to know what is going on, how the system works. But I think here, specifically in terms of an algorithm, not only publish the formulas, but you'll find quite often that the implementation makes a difference. Up to the point that if you have the same implementation, same source code moving from, let's say, a Windows system to a Unix system, or from an i7 to a Xeon server, it behaves differently. I'm talking about more that kind of transparency. Of course, but that is user-friendliness and transparency to the student. What does the student have to expect? For instance, how many items will there be in the test? Will my next item be a bit more difficult or easy? That is information that is a form of transparency too, and is sometimes badly needed. But most of those things about, especially about user-friendliness, I think that is responsibility of the manufacturers of the players. And yes, if a player needs information to put that on the screen to the student, and that needs that information from the algorithm, yes, then we have the responsibility to provide that information. What I think is transparency mainly in making sure that all people who have the right to inspect the source code gets it. Not by asking 5 times, but by presenting it to them. To everyone who is interested in having a good look. Does that answer your question? Yep.
More or less. There is time for another remark.
Yes. So I have 2 questions, if I may. One is, I think it is So having a cat is very optimistic in many ways, because I think it sort of assumes we have this flexibility and a lot of these resources that quite often not necessarily available. And so many of the people who work in operational testing often start with a rat, not a cat, right? A rarely adaptive test. And there's been lots of discussion at the conference about it. Rats don't grow up to be tigers. They grow up to be poison-spewing Komodo dragons. And so my question to you is, if a testing program starts really with a rat more so than a cat, what would you say is really the single largest danger in the development process in your experience to becoming a tiger rather than a Komodo dragon?
That is a nasty question. I would say this is a matter of communication with, in my case, an external client. Make sure that he has his priorities correct. And usually this rat comes from this little wash basin that you simply don't have the means to develop the items that you need. Maybe because of the flexibility and the that demands on the user interface, you're limited to things that don't work. But then I would say have a good look at, let's say, a multi-stage test, which I definitely think belongs to the cat family, if you do it properly.
And then the second question was, we're now in an age where a lot of us are working with Google Analytics and Activity API, where we're collecting an avalanche of information on our examinees. That, you know, we're looking at data and databases that are no longer in the terabytes but petabytes, and analyzing that kind of information is becoming exceptionally burdensome, not only on learning science to digest that information in terms of the integration of how testing is working, but also how data science can inform us, the psychometricians, about the subsequent development into tigers. So looking into the future, what would you say in terms of that kind of information that we historically have not had access to, do you think is the most valuable piece of new information that we could leverage to grow tigers?
May I ask you to give a short answer?
Yeah.
Because we are running out of time.
We are running out of time, yes. Well, maybe we should realize that this is a different technology. We're not talking about a test, people setting into a computer room or putting it behind a screen and say to the student, well, now you do this test, you take it. Maybe it's a question of doing both. Maybe it is a competing technology. And yes, maybe this will endanger the tiger. Just as in real life, the tiger is also endangered. Who knows? Let me be optimistic and say, well, if it brings progress, we should do it. And if that means the end of the tiger as a species, well, as long as we're talking about those digital tigers, I can live with that perfectly.
Okay, thank you. Let's thank Angela again. She will be around here and you can talk with her, of course. And I hope you enjoyed the session, and I will close it by this, because there is a next one now. Duan Li will start, I think. Thank you again.
Hey, good morning, everyone. My name is Duan Li Yan, and a group of us are going to give a presentation for adaptive multi-stage testing. And so far at this conference, we have heard lots of discussions, presentations on multi-stage testing. Mark talked about CAT versus multi-stage testing. We had early career award winner working on multi-stage testing, and we just heard Angela talking about multi-stage testing. And also there are sessions on multi-stage testing. So obviously we've seen the multi-stage testing research and application has been getting more and more popular. And this is also happening in US and internationally. So today we're going to talk about several topics around multi-stage testing, including new developments and challenges and solutions. So multi-stage testing becomes popular is it has a great improvement and a lot more advantages over the traditional linear test. And so that becomes assessment design of choice for many of the operational programs. In Mark's talk, he mentioned about CAT versus multi-stage testing. And in theory, CAT is going to be performing better than multi-stage testing in statistically and also ideally. However, when we are in practice, when we have to implement operational adaptive testing, the CAT, as Mark mentioned, becomes bad or red. And so there are lots of things to be considered and lots of complications for CAT to be operational deployed. That includes the complicated item selection and the usage of item pool, content constraints, test development specifications, and also financially to administer a CAT in reality. So for the test with the similar advantage, multi-stage testing provide a framework to have easy implementation and does as good as CAT in reality. And so the comparison actually in reality should or would be a BAT versus MST or red versus MST. So I also imagine that as computer science continue advance rapidly, the multi-stage testing, so if I know how to do this. So this is a basic multi-stage testing with 2 stages. The first stage is routing module, and then the second stage with 3 different modules from easy to medium and to hard. And we have introduced the design and comparisons applications in the reference book, Computerized Multi-Stage Testing Theory and Applications. But also I imagine that once we have more advances in computer science, the modules can be changed to have fewer items in each module and also more number of modules at each stage. Once we get to the stage that we have 1 item per module and with many stages, which is a CAT. So that's, we wait for it to come. So in this multi-stage testing new development, what we did is from what we did before, the multi-stage testing theory and applications that up to 2014, we have focused on software development. So today, we're going to introduce software. And one of those is using R. It's include R packages to do CAT and multi-stage testing. And we call it MSTR. So those are already available in the R community. And the book has lots of discussions and descriptions for the R software. It includes IRT basic introduction, includes the CAT introduction overview, include the CAT-R and CAT-R examples, and multi-stage testing overview, multi-stage MSTR, how to use it, and examples using CAT-R and MSTR. So I'm going to, first of all, talk about the MSTR. And this is a presentation. So can I get help? switch to the, so this is different from mine. Can I get help? Thank you. So the MSTR presentation actually should be presented by David Magis from University of Liège in Belgium. Unfortunately, he has a schedule conflict and he cannot make it, so I'm going to talk, not this one. I'm going to substitute him to give this presentation. And if you have a question, then you can ask him. No, this one.
PDF?
Hmm?
PDF?
Yes. Yes. I wish I know Japanese. Pointer, I do this. Okay, good. So you can see this is an R package to generate multi-stage testing designs. And for comparison that we've already seen from the last 2 days, that if you want to design a multi-stage testing, you want to explore, first of all, what is the goal of your testing and how you're going to build it. So the R packages will provide this environment for you to do lots of simulations, and so you can find out which way is better, how many stages you want, how many modules, and how many items in each module, and do quite some exploration. So this is really a useful tool, and we're thinking to provide this kind of environment so for you to design your own multi-stage testing, and then that's necessary for research and study before your actual implementations. So, so then the first part I'm going to mention really quickly about multi-stage testing, and then main thing is to talk about MSTR, then including item bank modules and passes, and the main function random MST, and then example and some future work. So multi-stage testing is an adaptive process for administrating a set of items, we call it module, in successive stages, and using optimal module selection among the variables or passes, routing. And so the research and application are increasing internationally. So we're going to mention this in the IRT framework. So the R package is called MSTR, has a hierarchical structure with functions for the basic IRT computation, including the probabilities, information function, and ability estimation, standard error computation, module selection, scoring, reporting, and also simulating item responses. And all of those functions are embedded in the main function of random MST. So we can see there are several levels for this design. There's a top level that including the top level functions, very general functions. At MST level, there are technical functions, MST specific functions, and evaluation functions. If you have used or heard about CAT-R, there are lots of similarities from MST and CAT-R because that's how it's get developed. That CAT-R was developed for a while. It's already, and lots of people, researchers have used it, and MSTR is just coming out. So at IRT level, there are item parameter generation, data generation, and scoring. And the basic level are some basic IRT functions. So when we do the adaptive testing, we have to have item bank. We have to build modules, and we have to design paths, the routes that we want to have this test and test takers routed to the next level of test to give. So the item bank modules and passes are all part of the simulation if you need to do it. In this MSTR, item bank is a matrix with one row per item, and as many columns are needed for item parameters. So let's see. Most of the common situation are dichotomous IRT models, that 1PL, 2PL, 3, and also the polytomous item IRT, including graded response and partial credit model. They are all available. And then for setting the parameters in the R packages for the CAT also available. So this is an example of a 2PL model. So yep, supposedly we have 4 parameters that can be available for you to do your simulation. In this situation, we have 2 parameters. So that's A and B, and then C and D are fixed in the situation. And so the modules with that set of items are really merged and allocated to a specific MST in an MST. So we are also defining a binary matrix, and with as many rows as the item bank, and then 1 column for each module. So we're going to show you the example. So here is a module matrix that you can see. Module 1 holds item 1, 2, and 3. Module 2 holds items 4 and 6, and so forth. So that's an example. So setting up the matrix for the modules. And it's important to specify that which module belongs to which stage. So then we need another specification. So the solution is using a transition matrix. And the transition matrix is a squared matrix with many rows and columns as a number of modules. So that also has a corresponding modules and the stages. So here's again, for modules 1 to modules 2 and 3, if we're doing 1, 2, 3 design, then you can see that if it's for module 1, it goes to 2 and 3. Module 2 goes to 4 and 5. So that's the first stage, and then second stage on the left, and then same thing on the right. However, if you see that 4, 5, 6, so if we have 1, 2, 3, 4, 5, 6, 4, 5, 6 does not have the children, so they have zeros here. Okay, so this is the simple 1, 2, 3 design with 1 module first stage, 2 modules at second stage, and 3 modules on the third stage. And as we use the matrix to describe the modules, the item, and also the transition matrix. So what does the random MST look like? Well, in random MST, there are several parameters, input options. So true theta is the value of true ability level to be estimated. And there's an item bank. You're going to have one of those matrix to be the input for that option. And then you have modules. You input that matrix. You have a transition matrix. We did the trans matrix. And then the model. Which models you're going to use, 1PL, 2PL, 3PL, and then estimation maximum likelihood, or EAP, and things like those. Other options include responses and possible vector for item response for post hoc simulation. And you also need to specify a starting the option to select for the first module. And then doing the testing is when you do the estimation, and then final estimation has a list of options for final ability estimate. And it also includes some other options that if you see the MSTR description. So for the next level of detail is the start. The start will list specific options to select and administer the first module. That's what we call the start. And then the choices, possible options include random selection, include any selections forced by test developer, and also you choose the most informative module. In the test phase, as I mentioned earlier, the ability estimator are those common options that we've already know, including maximum likelihood, base module, and EAP, weighted likelihood, and total score. The module selection include maximum feature information, maximum likelihood weighted information, and posterior area weighted information, Kullback-Leibler, and posterior of KL. In the other possibility that we need to use and predefine are cut scores. We can define in IRT frame scale, or we can define in total or number correct scale. So then we call those cutoff. So from first stage to second stage, we need to select cut score or define it, or from estimated from the data. Now, the final list would include options for final scoring and reporting. So those can, possibility can be maximum likelihood and BM, EAP, and weighted likelihood, as we've mentioned. So it would be easy if we can see an example. Okay, so I'm looking at the timing. So the item bank for a large operational assessment, the data was is from the large operational assessment project that we did early. There were 100 items and administered to 133,000 test takers, and it was a linear test. So binary responses are calibrated under 2PL model. So the first row of the item bank matrix, first few rows is like this, that we have the items calibrated with the 2PL with A and B parameters. Then we have to have the MST design matrix. The design matrix was 15 items, so that we have 15 items for each module for the 6 modules. So it's an equal length module for this one of this example. So for 15 items in each module, that we could see the module matrix as we've seen before, that each item has assignment of which module they are in. So for example, item 1, 2, 3, they are in module 4, and item 4 is in module 2, and so that's a long matrix. Then we'll have the transition matrix to describe our module and the stages. So you see that the first module is, the first module goes to second and third, so 1, 2, 3, and then the second has the children of 4 and 5, and the third one goes to 5 and 6. So that's the design of the transition matrix. Okay, so then we are looking at the MST options. So the first module chosen as the most informative for starting the ability, that's first thing. And ability estimation, that for this example, we choose EAP. And the next module selection according to predefined cut scores. As I mentioned, those scores you can define cut score in IRT scale or number of correct scale, but there are some it's not the focus here, but you have several options to define the cut scores. So at second stage, module 2, what we define is for the theta, if it's less than 0, less than equal to 0, we route it to the left, lower, and if it's greater than 0, we route it to the right with a more difficult, higher level the modules. And so that's the first stage, after first stage. After second stage, we have 2 cut scores, and so one of those is defined as -1, and the other one defined as 1. So that's on the theta scale. And the final ability estimate is, estimator is used by ML. So what is the cut matrix look like? Because when we use random MST, we have all the parameter input, the options. So one of the option is the cut score. So the cut score is also defined with, described with matrix. So in this situation, you can see that on the from first stage to second stage, the cut score is 0. And then goes to the second stage to the third stage, we have -1 and 1 from those to infinity. So that's the way of specifying the cut score matrix. Okay, so pretty much the things we need for the random MST is in place. So in our environment, what we're going to do, we can assume that we want to estimate with the chosen theta level, for example, the true ability level at 0.5. How we do it? We specify the start. The start at this point, we gave theta as a 0. And a test phase, we gave a list specifying the method and the cutoff that we just defined. And then the final estimation, what method we're going to choose, is the ML. So this is an example of random MST. So we have the true theta, we have item bank that we defined, we have modules that we defined the matrix, transition matrix, the trends we defined, starting, testing, and final. So now we have all the inputs for the random MST, and then we can do the simulation to using this MSTR. So this is a few lines of output for the ones we just specified. And so in this situation, we have random generation of MST response pattern without fixing the random seed. Then you can also fix random seed. The item, so this is the output. An item bank calibration under 2PL logistic model. True ability level, we specified at 0.5. And the structure is 3 stages with 1, 2, 3. So that's the first description. And then we will see that on stage 1, we have how many modules and the number of items in each module and the responses that we just did. So for item number 1, 2, so 15 items, and then what are the items in that module? So 7, 13, 14, so forth, and the responses that we have. And given that we have a provisional ability estimate after the first module. And so for this situation, we have 0.23 with the standard error of 0.545. Okay, first stage is done. Second stage, and a number of module administered 3. Second stage is 2, right? 15 items, this is second stage. Third stage should be. Okay, second stage, actually this is, okay, so you understand what I meant. So those are the items and item numbers and the responses. And then the provisional estimate is 0.29. Stage 3, and those items for, the module number, sorry. Stage for the module number, that's the module. So for the second stage, if it's 2 or 3, so that's the number 3. And here is the number 5, 1, 2, 3, 4, 5, so the last module. So the provisional estimate is 0.376. Now you've seen that after the first stage, if it's above 0, which modules is it going to get? It's the 3. So that's the module 3. Then after that, we have an estimate of 0.29. Is this above or below 1? Okay, it's below 1. So then the estimate is the final estimate. So then I am going to show you what it look like. So you can use that output and plot it. So this is the route that with the ability for the 0.5 will take. So get module 1, 3, and module 5. So that is one example of using the MSTR. So there are lots of things to do continually. We have done the first step. And you can generate multi-stage testing response patterns with all different methods and different options. And we're still working on it with module and panel assembly And another direction is to implement tree-based multi-stage testing and tree-based computer adaptive testing. And then we could also have multiple pattern generations. So the current lay is MSTR version 1.0, and you can download it from CRAN. So, so this is the references that Magis and Barada did published their research, and we had our previous discussions in the reference in 2014, and the new one is in end of this year. So I have my part of presentation that I need to finish in about 20 minutes. So I would like to ask questions maybe after I finish the second part, if that's okay with you. Okay. Okay. So, we have the software developed. Now, at the same time, we are developing some other methodologies. So one of the things is a new probability-based classification. So when we go from stage to stage, we are routing the people from one stage to different stage with different modules, and that's classification. So in classification, there are lots of things we need to consider. So one of the methodology this presentation consider is some new approaches to do the classification. So when we classifying a student into one or several groups based on the previous test score that we call the computerized classification test, there were, it is tracing back to 1940 by weight, introduced the sequential probability ratio test. Now, sequential probability ratio test is a hypothesis testing, so that it does the sequential hypothesis analysis and testing. So from there, Spray expanded and further developed the sequential probability testing, and the classification has been implemented since 1970, including adaptive mastery testing by Kingsbury and Weiss, computerized mastery testing by Lewis, Sheehan, Smith, and adaptive sequential mastery testing by Walsh and Class. However, all the methods always result in an indifference region and in the decision space, which is that no classification decision or accurate classification decision can be made, and requires more testing item to reach a decision. So we are looking into the alternative approaches. So the problem is that when we have to make a decision, we have, for example, the student that if he passes certain score, hard cut, then you say he's a master. Without below that cut score, it's a non-master. So something like that, or certification and multi-stage testing routing. So the classification errors are in the situation that classification error can be big and small, and it's always something that we have to deal with to minimize the classification error. So this involves the fairness in lots of especially high stake and testing. If you're very close to the cut point, and what we're going to deal, how we're going to deal with it. So this has a broad application of classifying student into fail, pass, and fail. And common use is the hard cut-off classification. So we're seeking a decision process to improve the classification, minimize the classification error, and especially their potential implications. So we're introducing the classification probability-weighted approach. And so those are used, for example, if there's only one-time classification can be used and available, you have to make a decision and how to improve your decision. For certification and placement, as I mentioned, in multi-stage testing. So okay, so this is the hard cut. If it's we have a cut of X cut derived, then we based on that make the classification decision. So the indifference region enlarged here is that there is a cut lower and cut higher. If any score above cut higher, definitely probability master is 1. Below the lower cut is probability of 1 that non-master or no certificate. However, the middle range is a group that we have to deal with at this situation. So thinking back about classical test theory, an observed score is composed by a true score plus some error. And the true score, we can assume it's normally distributed with a mean and some standard deviation. So we can simulate a normal distribution with 1,000 and with a mean of 50, standard error of 10. And then we're going to use this to do, to explore, describe this method and how we're going to evaluate it. So we can find test reliability looking at the true score variance and total score variance and also the error variance. So for each student, we can assume the error is normally distributed with 0 mean and some standard deviation. And so then we can reformulate into looking at the variance, error variance. So in the population, we have a few parameters. Then if we're looking at the classification, and we can look at, this is the observed score versus the true score. If the true score, observed score is matching, that's either true negative or true positive. Otherwise, we have false positive or false negative. And so the false positive is when the error for the student with true score below the cutoff, and otherwise is that the error that we got classified and the true score, the error for the student actually it's above the cut score. So we can formulate some probability of false positive and false negative. So that's what are the things that we need to minimize. If someone has a disease and but observed test says that it doesn't, that's more serious than the without the disease but test positive. So that's a different rate. So in that case, we could have some weight parameters to weight the seriousness, which we call it cost. So the alpha beta choices, if they're equal, then we say both errors are equally serious and not serious. And otherwise, we could weight differently to say which option, which error is more serious than the other one. So then we can look at the test reliability and the error relationship. As the test getting more reliable, that you can see the rates are getting lower. So that's intuitively we could tell. And for a test with reliability of 0.5, and what is the error rate relationship with hard cutoff score for our sample of 100 with a mean of 50? So this is the mean, and we can see the relationship is like this. Okay, that's for reliability at 0.5. Now, if reliability increased to 0.8, then we can see the error rate follows the cutoff. Well, it's cross at where? Near the mean area, and then they are decreasing. So that's something that we know, and we need to go from here. So we could develop some probability functions, and then to figure out the indifference region. And so we can help the decision classification for the indifference region. So for example, the probability given a cut score with a test score of x, if the probability of the score bigger than cut can be described in this way. So that's the cumulative distribution, and that's if it's less than that, then it's 0, bigger than that is 1, and so there is a function associated with the indifference region. Okay, so then we're reformulating it, and the reformulation becomes similar here. So it becomes a function of x, it becomes function of cut. So in this case, what we need to do is to worry about a function associated with cut. And so the last part, this part is the density. So we can take a look of what does it mean. Okay, so with this f function, what we can do is association with the cut score is that if it's equal to the cut, okay, so if it's the cut is equal to the lower cut, remember the graph that we have indifference region and above 1 and below the lower cut and above the higher cut. So we can form the function to be associated with the lower cut and upper cut. And then what we need to do is in this region. Okay, let's reformulating it to be a function, a transformation of a y that takes the difference of the cut score, if we're worrying about the cut score versus the lower and upper versus lower. So that's the bigger range, and then each cut score where you have versus the lower score. Okay, then we rewrite it in a way that we could easily to handle. So what we're going to explore are two types of functions. One is quadratic function, this is the form, and the other is S-shaped function, and that looks familiar. Okay, so the proper probability for the quadratic function is can be written like this. And so then we can formulate with a C parameter here. And then C is between -1 and 1. And what is that? And that's the indifference region. So then we can choose different C's, and then that's how we're going to look for the f function. So with the function we have, and then the y's that we chose. So this is the functions of different C parameter. Then we can see for C equal to 0, basically it's a uniform weight for y in the group 2 indifference region. If C is greater than 1, and we're putting more weight given to the higher values, less chance for student of lower score in that group to pass. So then you can manipulate the function in the indifference region so that you can giving more weight for the people in the indifference region, how you're going to classify them. Then if C is less than 0, you're giving more weight to the lower value. So that is the idea. So we did some simulation, and with the sample size and the t-score, and then so that this is pretty descriptive, right? So this is the region, and we're looking at the cut score plus and minus 0.5 of the standard deviation, and then looking at different cut C parameters, and then we choose some cut scores. So I have limited time, so I cut a lot of the graphs from this slide. But the result is use of this kind of function with C greater than 0 greatly reduce one of the probability, which is false positive. But if C is less than 0, that reduces the false negative rate. And so here is one of the trend you can see for what I just said, the result. 35 minutes. Okay. So then at false positive at cut score near the mean, which is the 50. And you can see with the test reliability increases and the false positive rate compare with the hard cutoff with different C parameter. And then the false negative rate behaves like this for this 1,000 sample. And overall rate that if we consider the cost, but here the cost is 50-50, so that's something else that we could do that to look at different weighting of alpha and beta. Now the other thing is that we want to look at the misclassification rate versus the cut score. So at test score with reliability of 0.8, and this is the cutoff get up, away from the mean has a little bit higher and lower misclassification rate. So I'm not going to mention the second simulation. The second simulation is basically that you want to find a point and you do one direction instead of two direction classification. Okay, so the second group of function is S-shaped function. Well, this looks very familiar with everyone here. And then we do the transformation and we find a function of with y transformed like this, and then we also choose a t0 that if that at y0. So the density function is written like this, is with a k and the function written like this. And then so that if we note when the t is equal to, gets to, as it goes to 0 and 1, it goes to infinity. So that's exactly the region. So then we end up with two control parameters. One is the y and the other is k. Now, what the k performs, the k and effect for the function. Well, the k is behaving very much like the discrimination. As k increases, the curve becomes much steep. And so that's the k's parameter performance. Then for the y0, well, this is also look very similar because when you look at the first form, that's similar to our the most popular function. So this is one, the y at different level, and then this is the curve for that. And then so what you can see is that at y equal to 0, the curve is symmetric and the density peak is at the center of the bracket. But then if the y0 is less than half or above half, it's peaking on two ends. So that's what you can do with this to give a different weight for the regions that which way you want to classify. So the simulation is similar to what we did for the quadratic function. We use the plus and minus standard deviation, and then the result for the classification leads to much lower false positive, but higher false negative. So this is the exploration of some probability-based classification. So there are some similar graphs like what we see, but it's using different function. And then there's another simulation which is go one direction instead of plus and minus two directions. So the conclusion is that the piecewise probability function that we explored for binary classification of students on their observed score. The data are generated based on the classical test theory, and we explored false positive and false negative with their weighted combination. Those two families having features for different way you want to classify based on your purpose, and sometimes that you gave a certificate if people are above certain level that you need to give them certificate. And then for the people near the cut score, the hard cut score, how you're going to deal with it. And so that offers some alternative for you to consider that in your testing. So basically, we transform it and formulate it into some parameters, and by adjusting the parameters, you can give more weights or less weight or relatively weight at your choice to help you increase to deal with the indifference region. So there are lots of future work needs to be done to explore different samples and to perform other analysis. So basically, it's an introduction and some alternatives to deal with the indifference region when you have a classification need. So that is my talk. Thank you. So, okay, you have a question?
Yeah, I have a question.
Okay.
One of the things, maybe I have not seen it well enough. But you started with saying that it is unfair when somebody is just below the cut score. That is one thing. But what in the end, I think, and it was in most of your results, that the false negative rates are not changing anymore, are not changed when using this method. So maybe I did not see it so well, but the green curves for the false negative rates were lower than when you use your probability weighting. Is that, didn't see I that correctly, or?
No, the false positive and false negative, that with the increase of the reliability and the choice of the parameters for both group of functions, they reverse. So once you increase one, if you in the whole situation, and the other would be increased. So you reduce, this is like normal, that if you do the cut, if you move this way, you reduce one and you increase the other arrow. Now, about the fairness, it's not that, well, when I say unfair, it's not really saying unfair, it's trying to increase the accuracy for classification. And then, for example, if that you have a cut score, you want to give them certificate, and that's it. People above that score get certificate. What about the people that near the cut score? Do you want to deal with that? If you want to deal with, how do you deal with it? So that's dealing with that specific region to increase the, for example, you say, you know, one score below, or 1 point or 2 points below. I could consider, but how do I consider it? It's just 1 point or something like that, and how you're going to deal. So basically offers some consideration and methodology for people to do the consideration, to increase the classification for the purpose.
But then again, you did not succeed in that. In all instances? Or
well, that based on lots of things. Based on the alpha beta parameter, if you want to include the cost. Based on the choices, based on the 1,000 sample. So if you have a bigger sample, you have a different sample, you choose different standard error. So there are lots of things involved. So that we could not say it's definitely successful or definitely not successful. But I think that offers some useful tools for people to consider.
yeah, I agree with that. Thank you.
Okay. Yes, Wim. Oh.
Yeah, I wanted to ask, how does this compare to what Henry Chen and Kentaro Yamamoto did for the PIAC 2012 assessment? I recall there's also an indifference region where there is probabilistic assignment, and then they have high and low regions where you essentially have very high probability of getting the easy, medium, or difficult stage.
Mm-hmm.
So I think there are quite a few similarities that you could explore.
Sure. I could certainly look at their report, which I didn't know if there's, but I don't know that they look at the probability. Do they have derived based on a mathematical formula that basically there is, so the functions that we have is from in the indifference region, but didn't leave any space that's not covered by the mathematical function, so that you can choose options in the for the mathematical function, but I don't know the probability that what their probability is based. So I certainly can look at that and compare their approach and with ours, and also look into some other options.
I have difficulty understanding why this method is fair.
Okay, we're getting back to the fair. Okay.
You start out by saying that all these methods in different zones are unfair, but I can now be above your cut score and end up below the cut score with a positive probability. Why is that fair?
Okay, so for the fairness, this is maybe not the best word to use for me to use. It is very much of, given that one shot, how you're going to do it. There are lots of times that for the people in certain region that we couldn't make a decision, or we need more information to make the decision, we usually gave more items. We do some few other things. We ask questions. We do explore some, to gain other information. So this has a few assumptions. One assumption is that if we just give one shot, and with lots of constraints in it, what are the things that we should do? So that's...
So it's not fair.
Again, that the fairness is, what I meant is to increase the classification, trying to reduce the classification error.
But the problem actually, I mean, it's a straightforward statistical decision theory problem. There are many books with statistical decision theory. They don't specify these probability functions, they specify loss functions.
Yes,
and
so
then
that's...
you just minimize the expected loss and you're done.
Well, there's, for each thing, there are lots of approaches and many models, and there's situations that one of them is, or not one, some of them are better for certain situations, some others are better for the other situations. It's nothing is really general. I would say that this just offer exploration, trying to explore and find approach alternatives to in this situation. For decision analysis, this is with one of the professor that who's actually very much active in the decision society, Dr. Badesco, that using the probability to do the making the decisions.
Yeah, there are randomized decision rules, but those are entirely different applications and different problems.
Yeah.
I might sound a bit harsh, and that's
That's
intentionally.
okay.
No, because I don't think you're fair. You started out by blaming CAT. It's difficult. I mean, you get a monster if you try to create a CAT, etc., etc. You've done that before. You've heard that many, many times. This is an example of how difficult multi-stage testing is. You interrupt your test at an arbitrary moment, and then you make a decision with respect to an arbitrary cutoff score.
No, this
and
is
now you come up with an arbitrary decision rule. If you do CAT, you just keep testing.
Yes, in a situation if you cannot test, for example. So this is related, extending to our CAT. But it's if you have a situation that you cannot give more items, you just get one shot. So again, that I want to put less weight on the fairness, this word. This is that if you make a decision, you've already made a decision that for people pass and fail. How about the people in the region that you're not making, you have higher classification error. And so this is, again, one of the approach to explore that if those, maybe they're useful, maybe they're not. But I think that it can be useful for some situations.
Okay.
I've been working with licensure testing for most of my career, and the circumstance where someone is in the gray area of decision making happens all the time, every single day. And in an operational test, high stakes test, we have to affirmatively decide what we want to do with those people in a way that's fair and valid and legally defensible. One of the things that we determined was that we needed to base the decision only on the person's performance. And so and there is not an infinite amount of time to give a CAT test. So at the end of the time, if the person is in the gray area, we go back and look at their performance over the last N items, because if you've looked at any number of maps of CAT performance, the scores stabilize relatively quickly, and all you're really doing is shrinking the error band at the end of the test.
Totally agree.
And so the idea is to look back at a certain number of questions, and you can pick the number that makes sense to your program. And if the student's score has been above the passing standard the whole time, just give the point estimate of pass. If it falls below at any point in your region of checking, you can give the fail, because you can say affirmatively, based on their performance, they're not consistently above the passing standard for the end of the test.
I totally agree. And in operation, this is exactly that practitioners need to consider and to deal with making the decision every day. With the current that we have, the advantage, advantage that we could gain a lot of other information, the process data, and those are information that we probably didn't use as much before, but in the future, I'm sure those information can be used to help making the decision for the people that you are near the cut score, near the critical region. So thank you very much for all the feedback and the discussion, and it certainly helps us to consider the next step of research and activities. And the goal is trying to help our practice. Thank you.